In 3.6 Photoelectric Effect, we are going to talk about how when light energy falls onto shiny metal surfaces, electrons are ejected. And we are also going to do some calculations and talk about the uses of the photoelectric effect. This will be the end of Unit 3, Part 1, and then we are going to talk about the periodic table in the Part 2 of Unit 3. And here is a look at the things we are going to talk about. Honors students will have to use this equation, connecting photoelectric equation, frequency and Planck's constant to do calculations. Some calculations will have both the previous equation from 3.4 and today's equation. Regular chemistry students will have to figure out which of these equations are used for which problem. They don't need to do calculations. So the first topic is photoelectric effect and the E equals H times a frequency equation. So consider a metal surface with electrons just on the surface as shown in pink, and then suddenly we are shining a light on it like that. And then what happens is, if the energy of the light is a certain frequency or higher, photoelectrons are emitted. Any kind of electron emitted from the surface of a metal due to incident light is called a photoelectron. So you should write this down in your notes. When specific frequencies of light, electromagnetic energy, shines on a metal surface, the photons of light collide with metal electrons on the surface, causing some electrons to be ejected, kicked out. These are called photoelectrons. Here are the photoelectrons. This process is called the photoelectric effect. It's kind of like playing billiards when you hit one ball with another ball with the same or higher energy, the second ball moves. That's because both incident light and electrons are both particles. You can dislodge one particle with another particle. So remember, photoelectric effect is an example of light acting as a particle, like one billiard ball kicking another billiard ball. For photoelectric effect to occur, the energy of photons colliding with the metal must have the same or higher energy than the ejected electrons. If the energy is weak, then the photoelectrons will not be ejected. A similar example you may have noticed, some of the calculators we use in our class are solar powered, and if you have very weak light in our room, our chemistry room has no windows. If it's very weak, then there's no photoelectrons being produced in the silica chips on the solar panels on the calculator, and it won't be enough to generate electricity to do your calculations. So you will go under a bright light which will produce photoelectrons to do your calculations. Third bullet point, photoelectrons produced in this process generates an electric current. Not all metals do that. Some metals and metalloids, you will learn metalloids are metal and non-metal intermediate property elements. They can readily eject photoelectrons. Example is silicon. These are used to make solar panels. Second part of the notes, we are going to talk about the equation where we connect E, the energy of a photoelectron, multiplied by H, the Planck's constant, times the frequency of the electrons. There is a connection. The kinetic energy of the ejected photoelectrons is equal to the energy of the electron and is equal to the product of the Planck's constant and the frequency of the photon. So in this case, E is the energy of the photon measured in joules. H is Planck's constant. It is 6.63 times 10 to the negative 34th joules times seconds. Frequency is the frequency of the photon. It's measured in meters. Now let's look at solving some of the problems. So regular chemistry students should also look at this, because you need to know which equation to add when. So note that I will always give you the Planck's constant and the speed of light in a vacuum. And then these are the two equations. So let's look at the first question. It says UVA penetrates more deeply into the skin, but UVB more readily causes sunburn. These UVB photons travel with a frequency of about 1 times 10 to the 15 seconds. How much more energy do they carry? So you're going to find the energy, right? They're asking you to find the energy and you're given the frequency. The equation that connects energy and frequency is E equals HF. So you will be using this equation to solve this. What about the second one? If an electromagnetic wave has 6.64 joules of energy, so again we have energy, what is its frequency? Again, this one uses this equation. The third one, a photon with an energy of 5.1 electron volts, to be precise, will eject an electron from a piece of gold. What frequency and wavelength does the light with this energy have? So you are given the conversion of an electron volt to joules. So we are going from energy to frequency and wavelength, right? So first you will use this equation, energy to find frequency. And then you have to find the wavelength. Then you have to go from frequency to wavelength using the second equation. Okay, let's see how to do it. So here's the first equation, and then you're going to apply the values in here. H is a constant, and H is this constant value. Then you're going to multiply it by the frequency, which is this value. I'm going to write that down, and then you are going to do the multiplication. But when you do the multiplications, seconds and second minus cancels out, and then you get 6.63 times 10 to the negative 34 plus 15. The answer is 6.3 times 10 to the negative 19th. So you're going to subtract 15 from 34. Okay, the second one, you're going to use the same equation, and then you're going to plug in the energy, and then you're going to find the frequency. So you can rearrange this equation this way by, let's see, dividing both sides by H, and then H cancels out on this side. Now you're going to add the values. So energy is this many joules, and then the Planck's constant is 6.63 times 10 to the negative 34 joules times seconds. And then these two are almost 1, and then joules and joules cancels out. And then you are going to divide these two like so, then you get 1.002, and then when you this goes to the top because it's negative, it becomes positive. And let me show this again. Second minus 1 is another way of saying hertz, so you can write it like this. This is the final answer. Final question. E equals HF is the first equation we are going to use and solve. you're going to rearrange it like this because we are asked to find the frequency here. Then energy, we know we have been given 5.1 electron volts. You can convert this to joules because 1 electron volt is 1.6 times 10 to the 19 joules. So you're going to multiply 5.1 by this value, and then you're going to divide it by the Planck's constant, just like this. And then joules and joules cancels out. And then you're going to multiply these two together. You get 8.16 times 10 to the 19. You're going to divide that from 6.63 times 10 to the negative third seconds. And then you get when you simplify this portion, you get 1.23. And to solve for the exponents, it will be 10 to the negative 19 minus 34, which means negative 19 plus 34, which is 15. So here is your answer. Second part, we are going to use this frequency with this equation to find lambda wavelength. We know the speed of light. Here we go. You rearrange it to find lambda, and then you're going to put the speed of light, then you're going to divide it by the answer we got here, and then seconds cancels out. When you divide 3 by 1.23, you get 2.44. Exponents, this will be 10 to the 8 minus 15, which is 2.44 times 10 to the 7th meters. I want you guys to practice doing these again at home. Okay, let's look at the full summary of this section. Atomic spectra and photoelectric effect main points. Spectra can be continuous or discontinuous. Discontinuous ones are called line spectra. Atomic spectra are spectra that result from atoms, emission or absorption. Emission is when electrons that jump to high energy levels emit energy when they go back to a lower energy level. Absorption spectra are what remains after electrons have absorbed energy. So emission spectra have the black background. Then number 5, we learned, this is 3.5 stuff. Spectroscopy is the use of electromagnetic spectral energy to see distant as well as microscopic objects. It's used in astronomy, chemistry, and medicine. Now, unknown absorption spectra and emission spectra can be compared to those of individual elements to identify the composition of a substance or an unknown substance. This is today's lesson 7 and 8. Photoelectric effect can be defined as the emission of electrons by metals when specific frequencies of light hits their surface. It is mathematically expressed using E equals HF relationship, where energy of photons is E and frequency of a photon is denoted by F, and finally H denotes the Planck's constant. Number 8. Light has wave and particle duality, as we learned in the atom topic when was that? Unit 2. Photoelectric effect is an example of electromagnetic energy behaving like particles, because it takes one particle to dislodge another particle. So when light shines on metal surfaces and dislodges surface metal atoms, then light must have particle properties. Okay, this is it. Please do the exit ticket that comes with this section. Thank you.